This book is the result of investigations that started 20 years ago. We've been interested in trying to prove something called the Lindelof hypothesis in twisted aspect. It's a growth of some ideas that were originated by the Finnish mathematician Lindelof in the early 20th century. And in the course of studying them, I and my collaborators have been led to all sorts of constructions that are brand new. And in the process of making those constructions, we've found that we need to branch out to other parts of mathematics and bring ideas that are from radically different areas of math into our study, and that if we do that, certain symmetries ought to hold. Certain things that look very different should be equal to other things. And I and my collaborators, Dan Bump at Stanford and Ben Brubaker at MIT, set out to prove that in one case, these equalities held that were a sort of manifestation of a very deep symmetry. My collaborators and I realized that something should be true, and we realized it by thinking about some abstract heuristic principles that we thought should govern the behavior, and then we generated computer files, literally thousands of pages of files that showed us that in many instances what we thought was true, and we could prove it. And then we set out to do a general proof. And it was really amazing because we thought it would be something that we could do with methods that we had, and we quickly realized that it was a much more challenging problem and kept thinking of new ideas and trying the new ideas out. And each new idea got us a little bit closer, but still far from the general goal. And this process went on. I would meet every week with Ben Brubaker at MIT, or he would come to BC, and we'd work at least a day a week together. And then, of course, we'd always be working separately as well. Parts of the project were spun off to Dan Bump at Stanford, and he was able to contribute to one part while Ben and I were working on a different part. And Dan also was generating a lot of computer data that was very useful to us. And we kept on working and working. And after a year, we weren't out of ideas, but we also were very far from a proof. And in fact, it wasn't obvious to us that we would ever get to a proof. And it was sort of like you're climbing a cliff. And you've been climbing the cliff for a year, and you realize you're really far off the ground. Ben was a young guy, doesn't have tenure. He's now an associate professor at MIT. And we'd invested a year of our intellectual energy, and we were far off the ground, but we were also still far from the top. But we never ran out of ideas. And Ben and Dan and I would get together, we'd share ideas, different parts of the project got divided up in different ways as we went along. And finally, it was just amazing. All of a sudden, there was one last idea, and we tried it, and it worked. And all of a sudden, we realized that we had reached the top. It probably was about 2 years of effort for each of us in total to produce the theorem that forms the first 2/3 of the book. And then the last third is yet another intellectual enterprise that went a bit more quickly than the first one, thank goodness, but also is very interesting because it connects ideas in number theory to ideas in mathematical physics. And there we realized that we could use methods from statistical mechanics, methods that were introduced by physicists to study things like phase change, to model sheets of ice, and we realized that we could use those methods to study phenomena from number theory. And in one case, maybe sort of the easy case of our cliff climb, we could use something from physics called the Yang-Baxter equation to give a new proof of the theorem that it took us 2 years to prove. Unfortunately, that's only the easiest case of it, and I don't know how to use those methods from mathematical physics to do the general case, but it's quite intriguing to see methods from mathematical physics coming up in number theory. So one thing which was surprising about this project was that the known methods just didn't really get us very far. We had to somehow create the whole edifice from the ground up, and we weren't able to borrow ideas from other fields effectively. We weren't able to see work that other researchers had done that would pertain and really allow us to get farther. And it was this very, very exciting period of feeling like you're creating a whole new approach to studying these these problems, and an approach which we hope will go farther towards the Lindelof hypothesis, though that may be a generation, but somehow that we were creating new ideas and bringing ideas together that had never been brought together before, and then building the next stage of the building, and finally we got up to where we were able to do what we had set out to do. But it was really one of the most exciting moments of my life to feel that I was creating so much that was very different from what anyone had ever done before. Physicists have done a tremendous amount of work on ice models, and statistical mechanics is a well-developed area. It's an intriguing question as to whether some of the objects that we're finding that are very natural in number theory also have some connection to the physical world, or but the methods we use could be applied in their context. We have something called commuting transfer matrices, and there are physicists that have devoted a lot of energy to finding commuting transfer matrices, and ours seems to be the first example of commuting transfer matrices that don't come from the established procedures of mathematical physics to establish them, things like the Yang-Baxter equation or the Bethe-Ansatz. And the question as to what that means, I think, is an interesting one. I don't really know. We've created this version of ice that we call metaplectic ice. Ice, of course, is what we know as H2O, and physicists model ice by thinking of a thin sheet of ice and thinking of the oxygens and the surrounding hydrogens and making sort of some kind of a pattern that captures that and attach something called a partition function that allows them to study it. And all of a sudden, we have some sort of lattices that are like the ice models that physicists use, and we have a partition function, but it's very, very different, and yet it has some properties in common. So there's no physical manifestation of metaplectic ice, the kind of thing that we've created, and yet there are so many things that are true about it that it's intriguing to ask if there is some connection, or if the methods that we introduced could be used in another context. There are short-term outcomes from our material which are very exciting. A lot of people are getting interested in it. There's going to be a special semester at Brown in spring 2013, and people are coming from all over the world to work on combinatorial representation theory and number theory and use some computer methods from SAGE, which is a very sophisticated computer program for doing high-level computations. So it's very exciting, and a lot of people are working on the kind of connections that our book illustrates. There's also going to be a conference in late 2013 in Canada at the Banff International Research Center, which is about our stuff and also in the context of geometry and in the context of physics. But there's a longer-term goal as well, and that's to take our ideas and apply them to the Lindelof hypothesis that I mentioned earlier. And that's what we've done is just somehow the very beginning. There will clearly need to be new methods introduced to make progress, but I think our work gives hope that maybe it will be possible to do that. I think, as I said, it might be a generation away, but I think there's really hope. And our book illustrates that combinatorial methods can be combined with number theory and combined with geometry in interesting ways to establish things. And then the hope is to go even farther and to do it in cases where there's a little bit less underlying mathematical structure, replacing Lie group by Kac-Moody, symmetrizable Kac-Moody Lie algebras. And if you could do it in that context, you would have a tool which could be applied to number theory to handle moments of L functions in a way that no one can do. And I think it would be just a dramatic development for the field. So that's, of course, my hope, but I hate to be too optimistic about it. It's pretty hard stuff, and on the other hand, it takes some talented people to come into the field, so some great young people to bring their energy, and I believe in young people, and I believe in more established researchers as well, and I hope all together we can make some progress over the next couple of years and beyond, and get somewhere towards proving those things. I'm very excited that this book is coming out in Princeton University Press. It's a series that captures mathematics that people hopefully will want to read about and consult for many, many years. And so, in fact, Princeton University Press agrees that all the volumes in the series will be in print indefinitely, Mathematics is different from experimental science, where sometimes one understanding is replaced by a more sophisticated understanding, and the old understanding is proven to be a bit inadequate, such as I learned that if you have an atom, you have the nucleus, and then you have the electrons orbiting, and now we have a much more sophisticated understanding of the way electrons fill up the space around the nucleus. But in mathematics, it's different. Each generation builds on the generation before. Each researcher builds on the researchers before. Having a library with a long-standing collection with books that go back 20, 30, 40 years is critical to every researcher in mathematics. So this book getting in this series means that it will be here not just now and not just in 5 years, but that the book will be in print and available for generations. And of course, the hope is that in generations to come, people will still be reading the book and find the ideas useful and valuable and ideas that stimulate them to do new mathematics. I'm excited to have our book published in the Annals of Math Studies. A bit humbled. Honestly, some of the people who've written books in the series are truly people I look up to and am in awe of, and it's really moving to be in the same series as them. And I'm hoping that it will inspire students to look at the book. It's not easy going. It takes a lot to read the first page, and to really work your way through it is something that's quite demanding. And I'm hoping that because it's in this series, especially, people will put in the time that's needed, because I think this is, as I was saying, the beginning of something that can go a lot farther and could really introduce some ideas to number theory that could change our understanding dramatically. I've always loved math, just from when I was very, very young. In fact, I was ill with appendicitis and flu when I was in very early grades, and so my mom brought home a bunch of books, and I got used to learning a little bit on my own at a very early age, and I found I enjoyed that. But I also have to say I enjoy and am interested in all human knowledge. I love math, but I love lots of other things too. I'm every bit as interested in history and politics and the way that human beings interact. Nonetheless, I have a real emotional connection to math. And when I got to college and saw the beauty of the abstract ideas and their power, the way that they could explain things about numbers, about other mathematical concepts, I was really hooked. And, I think, like I said, I like many things, but math is something that just is something I really care about a lot. So to both do it and to interact with young people and share that with them is something that makes me very happy.